Welcome to This Explainer. Today, we are diving headfirst into the fascinating physics of kinematics, specifically, how things move in a straight line. If you've ever wanted to precisely map out, predict, and really analyze exactly where an object is going and how it gets there, well, you're in the right place. Let's jump right into it.
Here's our roadmap. We're going to quickly hit the basics of motion, translate all of that into equations of uniform acceleration, visualize it through graphs, apply it to gravity and free fall, and finally, look at how we put motion to the test in a real-world physical experiment.
All right, Section 1, the basics of motion. Where and how fast?
To kick things off, let's think about a seemingly simple question. Can you travel 7 meters, but actually only end up 1 meter away from where you started? Well, yeah. Imagine you walk 4 meters east, turn around, and walk 3 meters west. You physically walk 7 meters total, sure, but it creates a really interesting knowledge gap if someone just asks, how far did you go, without establishing where you actually ended up.
And that right there perfectly illustrates the critical difference between two core terms in physics. Distance is a scalar quantity. It's the total actual path you walked, and it's always positive. In our example, that was 7 meters. But displacement, that's a vector. It is just the absolute shortest straight-line distance from your start position to your finish position, and it absolutely must include a direction. So your displacement is simply 1 meter east.
Let's ground this with a map of Tom and Muheba. If you start at point P and you need to get to point U, your distance is that winding, block-by-block path you have to walk along the grid lines. But your displacement? It's just the direct, shortest path straight line from P to U, cutting right through any buildings in the way.
Now, this crucial distinction applies directly to how fast we are going too. Just as distance and displacement are different, speed and velocity are fundamentally different things. Speed is a scalar. It tells us the rate of change of your distance regardless of where you're heading. Velocity is our vector. It's the rate of change of your displacement, meaning it always has to have a specific direction attached to it. So, 12 meters per second is a speed, but 12 meters per second east is a velocity.
And when velocity changes over time, we get acceleration. It's pretty straightforward. If a car speeds up from a complete stop to 30 meters per second over the course of 5 seconds, that's a positive acceleration. The velocity is actively increasing. Conversely, if that same car hits the brakes, going from 30 meters per second down to 0 over 5 seconds, the acceleration is negative. Its velocity is dropping. In kinematics, we generally call this negative acceleration deceleration or retardation. Moving on to Section 2. Equations of uniform acceleration, predicting the future. Now that we have our core variables clearly mapped out, we can unlock the mathematical equations that allow us to actually predict an object's future motion.
When an object's acceleration is uniform, meaning it remains completely constant throughout the motion, we rely on these 4 standard equations. You've got U for initial velocity, V for final velocity, A for uniform acceleration, T for the time interval, and S for displacement. The key takeaway here is that if you know just a few of these variables, you can manipulate these equations to solve for whatever piece of the puzzle you're missing.
Let's put this into practice with a real-world scenario. Imagine Selena is driving along at a velocity of 10 meters per second. Suddenly, a cow wanders into the road, which means she needs to stop, and fast. If the deceleration of the car is a constant 2 meters per second squared, what is the distance her car will cover before it safely comes to a complete halt? Step by step, we can solve this effortlessly. First, let's identify what we know. The initial velocity, u, is 10. The final velocity, v, is 0, because she's coming to a stop. The acceleration, a, is -2, since she's decelerating. We need displacement, s. Looking at our toolkit, we grab the third equation. V squared equals u squared plus 2as. Plug in our numbers, and we get 0 equals 10 squared plus 2 times -2 times s. That simplifies to 0 equals 100 minus 4s. Move that over, 4s equals 100, divide by 4, and boom! She needs exactly 25 meters to stop safely. That is the power of kinematics.
Numbers are powerful, but mapping these changes visually really lets us comprehend an object's entire journey at a single glance. Section 3. Visualizing motion through graphs. Let's map the journey. This table is essentially your ultimate cheat sheet, consolidating the rules for our 3 main graphs. For a displacement time graph, the gradient, or the steepness of the slope, represents the object's velocity. For a velocity time graph, its gradient gives us the acceleration. But here is the really incredible part. If you calculate the geometric area under a velocity time graph, it gives you the object's total displacement.
It's a beautiful intersection of geometry and physics.
Okay, Section 4. Gravity and free fall. Motion in the vertical. The crucial thing to remember here is that everything we've just learned about horizontal motion perfectly applies to things falling straight down, too.
Free fall is just defined as the motion of an object under the influence of gravity alone, completely ignoring air resistance. Because gravity acts uniformly near the Earth's surface, free fall is really just one-dimensional motion, with a constant acceleration pulling objects downward at roughly 9.81 meters per second squared. We represent that acceleration with the letter g.
Because the acceleration is uniform, our four standard equations still work perfectly. We just swap out a for g. Say you just drop a ball from rest, meaning initial velocity is 0, and let it fall for just 5 seconds. We use the equation v equals u plus gt. 0 plus 9.81 times 5 gives us a staggering 49.05 meters per second. That means in merely 5 seconds of free fall, an object is plummeting downward at over 49 meters per second. To put that in perspective, that is over 100 miles per hour just from a 5-second drop.
We have the theory, the math, and the graphs, but physics is an experimental science. Section 5. Putting motion to the test. Practical 1. To truly solidify this stuff, we have to test it in the physical world.
In Practical 1, our aim is to analyze the motion of an object to figure out its displacement, velocity, and acceleration using actual experimental data. So we're stepping away from hypothetical math problems on paper and using a dynamics track and a moving trolley to generate some tangible, real-world results.
The procedure brings all of our concepts perfectly together. By simply releasing the trolley from rest and recording its displacement over specific time intervals using a sensor, you generate a real data set. From that data, you can calculate the average velocity and acceleration yourself, and most importantly, you can then plot your own displacement time and velocity time graphs, comparing your real-world experimental values right back to the theoretical predictions we've been talking about today.
It is always so rewarding to see the math perfectly mirror reality in those experiments. But as you review the graphical results from a trolley test like that, I want to leave you with a deeper question to ponder. Why is it exactly that the flat, geometric area under your velocity curve magically translates into the real-world distance you traveled? Hint: think about what literally happens when you multiply the units of the two axes together. It's a profound mathematical truth tucked inside a simple little graph. Thanks for joining me on this explainer, and keep questioning how the world moves around you.